Welcome back to our video module on dynamics. Today, I'd like to revisit our cart problem. So the last we left it, it had a spring here and it would go up a certain distance, and we saw conservation of energy as the bearings heated up, as the air diffused. But let's say we have a pure system where there's no air and there's no friction. In that case, you're going to see it go back and forth and back and forth. What I'd like to do today is I'd like to say we're going to start it. We're going to start the cart by pushing it up the hill. All right, and initially I'm going to start the cart. I'm going to start pushing it up the hill to its height h, and it's going to be hard work, and it's going to take me about a minute of hard pushing, slowly, surely getting it up the hill from height 0 to height h. And during that time, I'm giving it a certain amount of energy. The energy I'm giving it is mgh. And in order to do that, I'm doing a lot of work to make that happen. Now that's scenario one. Scenario two is I call my friend Clay over and I say, hey Clay, can you push this up? And he's pretty strong, so he takes it and he pushes it up in about 8 seconds. Now, the energy that he's given this cart is exactly the same as the energy I did. However, one senses that he's stronger, that somehow measuring what happened just by work doesn't quite give the whole picture. And in fact, this isn't too different from another experience I've had. So I used to race mountain bikes, and you can imagine, you're first place, you're killing the field, you're doing great, and you get to the top of the mountain, and you're a good 5 minutes faster than the last place person. Now, let's neglect air resistance and neglect rolling resistance and say really the bulk of the energy, the work you've done, has been to gain altitude. You and that last place person have done the same amount of work. You have the same energy at the end. Once again, it seems that energy isn't quite giving you all the information you need. Or another example can be found in everyday experiences like driving a Ford Pinto or driving a Ferrari. Well, maybe your everyday experience is different than mine. But you can imagine you're sitting at a stop sign or a stoplight, the light goes green, and both of you go to 60 miles an hour. And let's pretend for the sake of argument they have the same mass, both cars. You both go to 60 miles an hour. You've both done the same amount of work. You have the same amount of energy. However, the type of experience you have driving or being a passenger in the Ford Pinto is very, very different than the type of experience you have in a Ferrari. Once again, work doesn't seem to quite sum up the experience. Finally, in the evening times, I like having a pot of tea, normally licorice spiced or something like that, and my oven has 5 burners. Now, I usually do the power burner, the one right front and on the left, because it gets that water boiling the fastest. Now, I can use any one of those 4 other burners. We're still taking the same mass of fluid with the same thermal capacity through the same change in temperature. So the work is the same. It's going to have the same amount of energy at the end. But we find that one of those burners does a much faster job. This introduces the idea of power. So because this type of thing happens so much, we can intuitively grasp this idea. We've defined power as work per unit time. So in all these cases, the work that was done was the same. But if we changed the amount of time it took, it painted different pictures. Another way to see this is W dot, or if you're dealing just with something that's moving, that's going to be the change, the rate of change in kinetic energy. This is where we saw the example of the Ferrari versus the Pinto. So the change in kinetic energy was the same, but the rate of change in kinetic energy was very different. So from your experience, you're feeling this. It feels totally different. And from the engineer's experience, she's looking at this, where one vehicle has a certain amount of rate of work that it can do, and another has a very different rate of work that it can do. This is what we refer to when we say horsepower. Finally, we saw something different when we were looking at our mountain bike. We took force times the rate of change of position, or the nice way we like saying that is force times velocity. Oh, not change in velocity, force times velocity. So you can imagine that while the work might have been the same, one racer was able to apply it at a faster velocity. We see the idea of power all around us. When you wind a watch, you take a great deal of power is exhibited to wind the watch up, and then it takes a long time for that same work to move all the dials. Or when you shoot an arrow, you take a fair degree of time to build up that energy. When you release, when you release the string, you're releasing this enormous amount of potential energy that's dissipated super quickly. As a result, you have a very powerful weapon in your hands. I hope this gives you a basic intuitive feel of what power is, and the brief summary of equations I've given you here are enough to get you started. Thank you, and I look forward to seeing you in our next module.